right? And so I think that'll be it for that also, all right? Then I'll have your guys' caffeine labs back for you tomorrow. Then you guys can finish up all the rest of the post labs and get those turned in along with the NMR packets. That stuff will all be due before you guys leave for Thanksgiving. Good. Got it? Yes? Yes. How are those NMR packets going? No, I know they're not easy. What's up?
Are you around for office hours later?
No, I purposely hide. You know me. I'm never here. I'm barely in my office. I never work. You know, just like every professor. You come in and do our 1 hour of work a week. Like, well, time to go to my beach house. And I say, we'll take the Ferrari today and go down to Key West. All right. So, but yeah, I'll be around. All right. Good. So lots of stuff to get finished before the semester's over with, though. Yep. All right. Now we were introducing the idea of alkynes, and what's the name of the game with alkynes?
Doubles.
Hmm.
You do double what you did with an L.
There it is. Okay. All right. So we're done with Alkyne chapter. Good. Moving on to no. Right. That's really all it is. What's the recipe to make an alkyne? What's the construction? What do we know about it? What are some of the properties? That kind of stuff.
It has a sigma and pi bonds.
Sure does. What do we know about sigma versus pi bonds? Sigma bonds are stronger. What else do we know? Why do pi bonds react before sigma bonds?
Because they're closer to the nucleus.
Pi bonds are closer to the nucleus?
Sigma are.
Sigma, so they react slower. Interesting. It's an interesting thought. Could be.
Is it because the overlapping p orbitals want electrons or are trying to give away electrons?
They can be. Pi bonds can be nucleophilic or electrophilic. That's true. True. What does chemistry? Where are the electrons in a signal?
Closer to the nucleus.
True-ish. Where are the electrons in a pi bond? Physically located in space.
In the p orbital.
Okay. Let me talk to you guys, Jim. So, remember, our pi bonds are basically hamburger buns, right? So if we have a carbon atom, okay, a sigma bond, right, the electron density of a sigma bond is in between the two atoms. Got it? The pi bonds are the hamburger buns. Okay? They're above and below the plane of the atoms. So tell me, why does a pi bond react first? What's one reason why pi bond reacts first? I didn't shade the bottom one.
Oh, whoops.
That's so wrong,
Maybe someone's secure one.
I'm sorry. I'm sorry. I didn't mean to pick on you like that. I just happened to walk over and see it, and I'm a smart ass. I couldn't help it. Do you? All right, so why would a pi bond react first then? Yeah.
Isn't it because like when something's gonna come and wants to react with it, it's gonna be the first thing that's gonna get hit?
That's exactly true, right? So imagine, right, if we have something reacting, right? And if we have something reacting, so we have a thing, whatever it might be, you know, some kind of base with a minus charge, right? And that's going to be approaching our pi bond. What's the first thing it's going to run into? Physically, it's going to hit what bonds first? The pi bonds, right? Why? Because they are above and below the plane of where the sigma bonds are, right? We have to kind of weasel our way between, you know, through those pi bonds to get to the sigma bond. And that's just not really how things are going to work. Got it? So the pi clouds sit above and below, right, the plane of the sigma bonds there, okay? And we have seen them, well, we haven't really seen them act as electrophiles yet. We will get to that though, right? We will see that for sure, the second semester of OChem. By the way, you guys are all done with your registration, right? Who'd you pick as your professor for OChem too? You're stuck with me again. No choices. Well, I don't know. Like I was, you know, I have had my schedule changed like 3 days before classes start. So we'll see, right? But anyway, so in the second semester, we'll learn a little bit about where pi bonds can act as electrophiles. Okay, but for the most part, we've been seeing them act like nucleophiles, right? Nucleophiles, right? How many times have I asked you guys about nucleophiles now in exams? All the times, right? Do you think it's important? Because remember, the first day of class, I summarized all of organic chemistry up for you. When I said what? Something negative attacks something positive. Right? What do we call something that's negative that attacks something positive? Oh. Got it. Do you think on the next exam I'm going to ask you about nucleophiles? No. What about the exam after that? Yeah. What about the third exam in the second semester of organic chemistry? No, that one not. Okay, so there's my promise, right? You guys can hold me to it. It's on, it's recorded, right? Dr. H, you liar. Okay, but that's important. We have to recognize how negative and positive things react. Okay. So anyway, now the question that I asked is, how do we build a pi bond? So what's the recipe for a pi bond? Mix 1 sigma and, excuse me, what's the recipe for a triple bond? Is what an alkyne, right? What's the recipe for an alkyne? 1 sigma and 2 pi bonds. Got it? Where's the other pi bond? Not above and below, but in the front and in the back, right? So remember, we're working on things in 3-dimensional space here, right? So we got the front, the back, the top, and the bottom. A pi bond's a pi bond, right? So we should expect that, you know, the 2 pi bonds and alkynes are going to behave very similarly to alkenes, and that's exactly what happens, with some exceptions, okay? And we'll talk about some of the exceptions today, all right? Crap, I forgot the book. Uh-oh, time to just make it up. Ugh. So we have things called H bonds that are invented by Dr. Anyway, so when we're dealing with an alkyne, right, we're going to react the same thing twice, right? And so we learned about our hydrohalogenation, right? What happens if we add HCl, HBr, HI, right? What happens if we add those to an alkyne, right? And we went through and we took a look at the mechanism with that, and we went through and we did this here, right? And we got to that point where we made a geminal dihalide, right? That's one of the rare cases where we can generate our geminal dihalide, right? There's really no other way that we have of constructing that, or that we've learned about so far yet, right? So if you guys see that geminal dihalide, you know it had to come from an alkyne to begin with, all right? So there's that, okay? And we learned that we can take that geminal dihalide and we can kick it back to an alkyne using something weird, some really weird reaction here. It's where we have a strong base that grabs a hydrogen that's next door to a leaving group. Wow. What do you guys want to call that? Yeah, we'll call it an E2. Sounds good. You guys got it? It's the same mechanism happening here, but twice, right? Now, we did mention that we can only do this with certain bases. We have to have a really powerful base. Our T-butoxides and our alkoxides, ethoxide, these kind of things, they're not really going to be quite strong enough to take us all the way to an alkyne. They're just going to make a big mess is really what it comes down to, okay? But this guy here, sodium amide in ammonia, will take us all the way down to an alkyne, okay? Yeah, what's up?
Did you say that the geminal dihalides are only formed through hydrohalogenation? Or are there other ways?
That's the way that we know so far, yes. Yeah. And we do 2 subsequent eliminations to get to our alkynes is what it is. Got it? Yes? I'm gonna make you guys think. You ready? Promised I would make you guys think on the video, right? We marked a couple of examples. So here we go. Time to think. Okay. How could I do that? Just to really think about it. Like super duper think. They're missing the best part. Why are you laughing? Said the crowd, right? You guys want a hint? Oh, okay. I guess not. All right, go for it then.
I'll take it.
Okay. Sorry, I thought silence meant no. Right? This is what we have to do. We have to make an alkyne. Right? What mechanism do we have to do to make an alkyne? Elimination, but twice. So what do we need?
Very strong.
2 good leaving groups, right? Now, what we've learned is that if the 2 leaving groups are on the same carbon, they will make the alkyne, right? Did I tell you that's the only case? No. Don't use the book that has answers in it. It's terrible. Right? Can you guys think of a reaction where you added 2 leaving groups, maybe not on the same carbon, but maybe next door to each other? Of what?
Like hydrogen or...
Well, we need to add 2 good leaving groups, right, next to each other, on neighboring carbons. Halogens, like what? Bromine, maybe? Do you guys know how to add bromines next door to each other? Okay. What do we add the bromines next door? Or what functional group do we add those bromines to? An alkene, right? You guys with me on this? So I need to make an alkene, then I need to put my two bromines, and then I need to do my elimination. Got it? So do it. So make an alkene, and do your halogenation, and then make your alkyne. Show me the mechanisms. I think something better than that. Got the right idea, let's get a better gauge. Could. Before my car look at, I can do that mechanism. I need to do an elimination, add a secondary carbon, right? So I pick my favorite base. If there's anything we learn, that eliminations are all about that base, right? Thank you. I'll be here all day. That's the appropriate response. Awkward chuckles. Thank you. All right. All right. So we did our elimination. We didn't need two, right? Now what? We said we have to get two leaving groups, right? We have to get two leaving groups onto carbons that are next door to each other, right? So we do our halogenation. We very importantly remember to keep things cold and dark. In the next chapter we'll learn why, right? Okay, remember we make our racemic mixture here, right? We make our wedge dash for both of those, good. And then we need to make an alkyne. And that's where our sodium amide and ammonia comes in. Right? Good. Do you guys catch what you did here? Take an alkane all the way into an alkyne. How does the mechanism change for your eliminations here as opposed to the one that we had in the video? It doesn't, right? We're just eliminating two different halogens. They just have to be next door to each other. So, I don't think we gave this a name last time, but these are halogens that are next door to each other, so we call that a vicinal, right? A vicinal dihalide, right? So geminal coming off of the same, right? Here we have vicinal. So now we got two ways of making an alkyne, from vicinal dihalides or geminal dihalides. Good? All right. Only going to take you guys one step. Ooh, that'd be an interesting question. Yeah, we'll get to it later. See what you guys come up for, both of those cases. So give me a good quick pause here to go run and grab my book, so I can make sure I'm on page with the others. Right that way. Right that way. All right. So for the first one there, what do we need to do? We got an alkene. What do we need to add to our alkene? We need to add what? An H and an OH, right? So we need to add some water. So if you just throw water in with your alkene, is it going to do anything? Nope. So we need a little umph to get it going, right? A little catalyst or something. So if we want to throw some water in there, right? Then we just give it some acid or something like that. Okay? So we have our acid catalyzed hydration. Fantastic. Okay. So we should just be able to do the same thing here, right? Woof! Organic chemistry is easy. What?
Wouldn't
Don't tell me I'm wrong.
there be a carbocation?
A what? No. Right? So remember, when you guys see a strong acid, sulfuric, HCl, HBr, HI, blah, 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 right? That's usually one of these flags that we have a carbocation that's going to get formed. And we're going to see shifts and rearrangements, weird things happening with rings to make goofy looking products, you know, just for instance. Okay? So can we do the acid catalyzed hydration there, the bottom step? No. Right? So we need to do a hydration, okay? We need to do a hydration that doesn't involve a carbocation intermediate. Got it? So what do we need? It's a very obscure reaction that we rarely ever talk about. What do we got?
Oxymercuration.
Oh, our oxymercuration, right? So what do we got? Hg, right? OAC2, right? H2O, right? And then we, whoops, sodium borohydride it up. Cool. What's the benefit of this? We go through a sumo mechanism. We add an OH to the most substituted side, but we don't, right? We don't see the formation of any carbocations. Got it? Good? Yes? Thank you. My favorite thing, and if you guys ever become teachers, your favorite thing is when you ask a question and everyone goes, right? I know, but Dr. H, you don't understand. It's like 10 o'clock. I still got another 2 hours from awake. Remember the whole benefit of going through the sumo mechanisms there, right? We end up adding things to the most substituted side, right? But we don't generate cations along the way. Very important.
Dr. H,
Yeah?
would it equally make the OH be on the other bond?
Correct, yeah. That's why I made the comment like, oh, I accidentally made a question that's a little bit more better than I thought it would be. So, yeah, you're right. But just for argument's sake, right, we'll say it makes that product there. But you're absolutely correct. These are both equally substituted. We would expect to see a 50-50 mix of both of those. Good. Thank you for telling me I'm done and wrong. I appreciate it. Yeah, anytime, Dr. H, would be happy to do that. All right, so now we have this question here, right? So we're going to do a subtle difference. Okay? So we're going to add some, well, let me get rid of that, excuse me. We're going to add some sulfuric acid and water, but we're going to add some of this to it also now, okay? So we're under these acidic conditions, okay? Well, we got some mercury in there, all right? You guys with me? Now when we do this, we would expect that our product would be something like that. Correct? Remember, when we're dealing with alkynes, we say that we do the same thing with alkenes but twice. Now I'm telling you guys something very important there. I'm not saying both things react at the same time. But I'm saying we do two alkene reactions. Do you guys catch the difference here? It's sequential. Does that make sense? So after we do our addition for the first time, that's what we expect to make, correct? And you'd be right. Except our product is actually this. Now Now I'm gonna make you guys think. I want you guys to tell me how we can do this, okay? I'll give you a hint. You already know the answer, okay? I'll give you another hint. Take a look at what's in our reaction mixture. And I'll give you a third hint. It has nothing to do with the mercury. As a shocker, we have a strong acid in here. Wow. What do you think, or how do you think strong acids behave? Like an acid. So what do you think is going to be the first step for this explanation here?
Acid base.
Probably, right? So I want you guys to see what you come up with. Yep. So what does that mean? Yeah, but on your molecule itself. And then what? Start with the acid. So, under acidic conditions, we're going to generate a negative charge. Right? So remember, I said you guys have acid, so use the acid. And he said, no, I'm going to use the base. I'm not trying to trick you guys. Didn't say it wasn't tricky, but I'm not trying to trick you. She was so shocked. Yeah, it's all good. Give it a reason to do that though. Give it a reason to do that though. Something will, absolutely. But I like this. I don't like what you did after that. This looks good. The zen of organic chemistry. right? Getting into the right mindset. And not getting intimidated just because things look differently. Do you guys catch what I mean by this? Do you? What do I mean by it? What do I mean?
It's the same thing we've been doing.
It's the same thing we've been doing. Just at what? Does it look different? Sure. Are we gonna approach it any different? No. Do you guys understand what I'm saying? What happens here? Do we have a double bond? Yeah. Do we have acid and water around? Yeah. Got it. What do we have here? Well, we got a double bond and we have acid and water around, right? Okay, so the same thing's gonna happen. Right? Are we adding an acid to a pi bond? Yeah. Okay, absolutely. What am I missing? Where would I put my carbocation? Well, they're both secondary carbons, right? Is that a secondary carbon? Yeah. Is that a secondary carbon? Yeah. Where am I going to put my double bond? My carbocation. That would be the place to start, right? Say, well, at the moment I don't really know. So what should your response be then? Put on both and see what happens, right? Okay, let's do that. Go technology. All right, duplicate. Got it. So we draw an identical compound, right? Fantastic. Amazing. Right? We might actually make a mistake while we're answering a question. Scary, I know. It's okay. Because we're going to go through and assess what's going on. Okay, so now we did a thing. We put the carbocation on two equally substituted carbons. If you'll notice, the winds have calmed outside, right? Not raining anymore. The apocalypse isn't happening, right? One of these has to be wrong. That's what I'm saying. Okay. How do we assess which one of these is better? What's the problem that we have to fix? We gotta fix a carbocation. Well, I don't think we've dealt with that at all. Have we dealt with those? Yeah, I don't think so. Have I told you guys how to stabilize charges? Huh? Oh, inductive effect. What else? Resonance. What else? Radius, electronegativity, hybridization, right? So how do we assess it here? The exact same way, got it? So, carbon in black versus carbon in red. What's bigger, the carbon in black or the carbon in red? Radius is the same. Electronegativity is the same. Hybridization is the same. Right? So it's got to come down to inductive effects then. Well, what's that oxygen doing to the carbon in red? Pulling electron density away from it. Oof, right? So the carbon in red is feeling even more positive because it's got an electronegative atom bound to it, right? That's not good. So we're destabilizing it, right? So it's got to mean that the carbon in black then, right? Resonance What do you mean? I don't see any resonance. That's twice in one day, alright. I'm on a roll. What do you see with resonance, that's what I'm saying.
That more resonant structures
That's true, but I'm asking where do you see resonance structures?
on the red carbon.
From where?
Well,
Right? Remember, we got lone pairs on our oxygen, don't we? Can oxygen draw or make a resonance structure like this? You bet. Right? Is that a resonance stabilized positive charge? Yes. Hey, look what else we made. We made a carbon with a double bond to an oxygen. Is that in our product? Oh, yeah. What's the problem we have to fix in our resonance structure, though? We have to get rid of that hydrogen, right? So what do you think is going to come in and grab that hydrogen? Some water. Sounds good. Cool. There we go. So, talk to me. What's unique about this reaction compared to pretty much every other reaction we've learned so far this semester?
It's harder.
It's harder. No, we've learned more difficult. I'm going to argue with it. Well, what do you mean by it's harder then? It's harder because it's the end of the semester, and we're tired, and it's wet outside, and what is unique about this? Hmm?
it looks different, it's just the same thing, like, you just have to do a little extra step with the resonance.
Sure. How many reactions have we learned where we can make, or what functional group did we make at the end there? Hmm?
The carboxyl.
She says it really quietly, so it doesn't get picked up on the video. What's that functional group at the end? C double bond O. Ketone, right? How many reactions have we learned to make a ketone so far this semester? Just one other one, right? This is only the second reaction we've learned all semester long to make a ketone. The only other one being from ozonalysis, where we cut double bonds in half and we chopped carbons off. Did we lose any carbons while we're doing this? Nope. Is this the only reaction we know then to make a ketone without losing carbons? Yes. Do you think that'd be an important kind of, let's say, pin to put in our brain there? Say, hey, look, now I can make a ketone at the most substituted carbon with no carbocation shifts and rearrangements. You guys got it? Ketones are going to be 4 chapters worth of material in the second semester of OChem. This is going to be one of our main methods of making ketones. Okay? Start from an alkyne, and then we can make our way to a ketone. Got it? Yes? You put Xanax in the water? What's wrong with you? You guys are all asleep this morning. We gotta keep them calm, there's a hurricane. All right. More Prozac, back up the truck, all right. Okay. Now look, now we've got a alkyne, right? We've got an alkyne that's at the end of a chain. Yes, a terminal alkyne. Good. I want you guys to think. Okay. What do you think we need to fill in the blank here? Right? What do we need to put here to make this reaction happen, to make this transformation happen?
H2SO4 and H2O.
Dr. H, how many carbons are on that thing on the left?
4.
4.
Mm-hmm. So I have a question for you guys. Ready? How do we do that?
Oxynucleation.
That adds to the more substituted side, right? Now we need to add an alcohol to the less substituted side. That's exactly right. This is our hydroboration oxidation, right? So what do we got? We got a hydroborate, so like BH3, right? THF, right? Hydroboration oxidation. Got it? This adds an OH to the less substituted side. How do you think this is going to behave with an alkyne? It's going to add an OH to the less substituted side, right? So remember, with an alkyne, you treat it like an alkene, but twice. So after the first thing, you make this. Got it? Then what do you think is going to happen? We see an alcohol bound to a carbon that has a double bond to it. But now we're under basic conditions. Okay? So come up with a mechanism to get to the product under basic conditions here. AOH is a strong base. What's a strong base going to be on the hunt for? An acidic hydrogen. Where's my acidic hydrogen? Where's my acidic hydrogen? Yeah, on the alcohol, right? So what's the first step? The hydroxide deprotonates the alcohol, right? Mhm.
So then there's that goes.
Right, that's the odd part about this one, right? So think about what I said for, where is it? Where's the carbocation? Oh, you forgot, you left it out, right? But think about what I said, you're like, you have to, the problem is that we have a charge. The problem is we have a charge. Say what it is. Resonance doesn't affect, right? We always say, I realize, because we put all resonance charge. How do we get from here?
You know, if I'm a co-pilot.
You're not gonna form a carbocation under basic conditions. Right? Okay, so how do we get from here? What's wrong? Hmm? Okay, what happens?
Oxygen deprotonates the alcohol group.
Okay, oxygen deprotonates alcohol.
No.
Oh, I'm sorry, it's my first statement. Like this, okay, I'll stop you. All right. I don't know, I could have been on to something with that last one there. Okay? What's the problem? No, that's not so much the problem. The problem is we have a charge, right? Do you guys see what I mean? We have a negative charge. How in the world can we deal with charges? Well, we have what? Inductive and resonance. You guys got it? Whether it's positive or negative, the approach is the same. You have a charge, stabilize it. Got it? So, can we draw resonance structures with this? Yes, we can, right? Good. What have we accomplished? We've accomplished stabilizing our charge, and we've made our double bond to our carbon, between the carbon and the oxygen, right? Okay, what's the problem I have to solve? Charge on the carbon, right? So we know we have to give that thing a hydrogen. Well, we have water around, so let's give it a hydrogen, okay? We will get to our answer there.
How do you know that the water will do that?
What does it turn into? After you deprotonate the water, what does it turn into? OH, right? So you end up making more of what you started out with. That's something good to pay attention to, right? You guys catch the difference here? What's the difference between what we did here versus the previous example? Well, here we're under basic conditions, right? This is important. You guys with me on this? We're under basic conditions. What charges do we see? Negatives, got it? Up here, we're under what? Acidic. What charges do we see? Are you guys ever going to see negative charges under acidic conditions? Probably not, right? You're not going to see a carbon with a negative charge under acidic conditions. I mean, that'll happen maybe in some rare mechanism, but not for our undergraduate OChem classes, okay? If you're under acidic conditions, carbocations get formed. If you're under negative conditions, negative charges get formed, okay? Now, what we've been doing, right? Tautomerization. Okay. So the relationship between these two things they are tautomers, right? Tautomers. We cannot stop this from happening. There is an extremely strong drive to form carbon-oxygen double bonds, whether it's under acidic or under basic conditions. Okay? My point being this: if you're doing a mechanism, okay, and you end up putting an alcohol on the same carbon where a double bond is, instantly it's going to tautomerize. Okay? You can't stop it, even if you really want to, okay? You don't understand, Dr. English. I needed to stop there. I don't care. Not gonna happen. Do you guys with me on this one? And that's good. It's good that that happens. Why? What functional group did we make here? What did we make? Not a ketone. An aldehyde. How many reactions have we learned about where we can make aldehydes? We've learned 2 now, right? Ozanalysis, which cuts things off, and we've learned, here we go, hydration of an alkyne. Okay? What's the only way we can make an aldehyde, though? When you do hydration of an alkyne under our hydroboration oxidation conditions. Why? Because alkynes can only be formed at the, aldehydes can only be formed at the end of carbon chains. Got it? So we have to add the OH to the less substituted side. What's the only reaction we know how to add OH to the less substituted side? You guys with me on this? So now we've got some methods to make ketones and aldehydes. And those are extremely useful functional groups. Okay? All right. Well, I hear them listening to music again, so that's a good sign here, right? So there's that. We'll end that for today. I'll see you guys tomorrow for lab, and the sun's even coming out. Fantastic. All right. So I will see you guys tomorrow then, all right?